Hi students, good evening to everyone. So this is Saurav and today I am going to discuss a very interesting topic of strength of material. The name of topic is deflection of beams. In every year gate examination there will be a minimum one question either of 1 mark or 2 marks. Means 100% one question you will get in gate paper either session 1 or session 2. So one by one we will discuss all the things over here, why we need to calculate deflection, what are the limitations of deflections, what are the different deflections or slope equations for various loading conditions for different beam, and what are the suitable methods for calculation of deflection and slope equations. So let me start from here. First thing is, what is our aim here? Our aim is to derive maximum slope and so what is our aim over here is to derive maximum slope and deflection equations for different kinds of beams under various loading conditions. Okay, so let me tell you one thing over here. Generally we all have gone through a term that is bending. What is bending? Bending is basically the deviation of the axis of the beam under the transverse shear force. Deviation of the axis of the beam. Which axis, students? Longitudinal axis. Longitudinal axis. Deviation of the axis of the beam under transverse shear load. TSL means transverse shear load. So again, deviation. Here one term has come, that is deviation. So what it mean over here? Suppose I am drawing a simply supported beam over here. Suppose the length of the beam is L and I am applying a transverse shear load of magnitude P over here. This is what this is the original longitudinal axis. If I apply a force of magnitude P, this axis will deviate like this, like this, like this. So this is, what is this? This is the new longitudinal axis. So this is known as the deviation of the axis. So from this deviation we are coming on the terms. If I talk about the deviation, this deviation is of two types. First one is what? First one is angular deviation. Angular deviation. And the second one is linear deviation. Okay. And the second one is what? Linear deviation. So one by one, I'm again repeating what is our aim in deflection of beam is to derive the maximum slope and deflection equations under various loading conditions. What happens generally, students, there are two criteria for designing of any machine component or a beam. First one is strength criteria and second one is rigidity criteria. According to strength criteria, what we do means our beam should be strong enough to resist the bending stress or the transverse shear force, or what our aim in rigidity criteria is to find out the deflection under the transverse shear load. This deflection should not be greater than the permissible limit of deflection, otherwise beam will failure. Another example, we can use the deflection equation to calculate the natural frequency of vibration or natural frequency of transverse vibration of shaft. Vibration you all have studied in your course theory of machines. Again we have discussed the bending. Bending is what? Bending is the deviation of the axis of the beam. Which axis? Longitudinal axis under the TSL. What TSL stand here? TSL stand over here, transverse shear load. What is happening over? I am drawing a beam that is simply supported and subjected to a point load acting over here. So initially this is our original neutral axis. After applying the load, the axis will deviate, and this will show the new longitudinal axis. So deviation is of two types over here. First one is angular deviation and second one is linear deviation. Angular deviation is nothing but angular deviation is known as slope, and linear deviation is known as deflection. A linear deviation is known as deflection. So one by one we will discuss about slope and deflection over here. So students, let me tell you some boundary conditions. Boundary conditions are most important things to calculate the slope and deflection equations for loading condition. But before going on boundary conditions, let me clear one thing over here. What is, yeah, what do you mean by angular deviation, or what do you mean by linear deviation over here? Simply, friends, what I am doing here, I am again taking the example of simply supported beam over here. Later on we will discuss some examples which have been asked in GATE previous years. 2-3 problems we will take from previous year GATE question papers. One by one we will discuss all things over here. What are the different methods for calculation of deflection of beams? What method you should apply to calculate the deflection of beam in minimum time? So suppose this is a simply supported beam. At one end hinge support, and at one end there is a roller support. I am assuming the length of the beam is capital L over here, and I am applying a force like this. Suppose force is P. What is happening over here? students, this is what this is our original this is our original longitudinal axis. This is our longitudinal axis originally. After applying force, this axis will deviate. This axis will deviate like this. This axis will deviate like this. So what is happening over here at ends? At ends, there is some kind of angular deviation over here, and this is the linear deviation. This is the linear deviation. What are these are the angular deviation. I am representing angular deviation here from theta, and linear deviation I am representing from y, or you can represent from delta. In some Indian books it is represented by theta, and some another book it is represented by capital Y. And theta is representing what? Slope is nothing but angular deviation of the longitudinal axis. So what this theta is representing over here, friend? This theta is nothing but theta is our slope. At one end, if the direction of slope is clockwise, another end the direction of slope will be anti-clockwise. In both the cases, magnitude will remain same. Sign will represent either clockwise slope or anti-clockwise slope. This vertical deviation is what? This vertical deviation is what? This vertical deviation is nothing but this is our linear. This is our linear deviation. This is our linear deviation, and this linear deviation is called deflection. This linear deviation is called deflection. Simply, in simple definition, we can define the deflection like this. The vertical gap, the vertical gap between the longitudinal axis of the beam before and after the application of the transverse shear force. I am again repeating, deflection may be defined as the maximum vertical deflection or the maximum vertical gap between the longitudinal axis of the beam before and after the application of transverse shear force. So this vertical gap will represent what? Deflection. Okay, uh, now we are moving forward from onto the conditions, boundary conditions over here. Boundary conditions over here. Boundary conditions. So for boundary conditions we have two types of beam. First one is what? SSB. SSB stands for simply supported beam. Simply supported beams. And second example we will discuss of what? Cantilever beam over here. So students, before going on any types of numerical problem, we must aware about the what are the boundary conditions. After knowing the boundary conditions, our calculation will make easier as compared to earlier one. And if you will go to any interview, there may be a question from the boundary condition related to deflection of beams. So first I am discussing about cantilever beam. Suppose this is our cantilever beam of length L, subjected to a point load at its free end. I am assuming the magnitude of load is capital W. What this line is representing? This line is representing, this is our what? Longitudinal axis. I am assuming this is point A, this is point B. Always remember, friends, at fixed support, at what? At fixed support, what is fixed support over here is point A. At fixed support, always slope will be zero and deflection will also be zero. But at free end, at free end, at free end, slope will not equals to zero and deflection will not equals to zero, but they will give their maximum value. What will they give? Maximum value. So you must remember, in case of cantilever beam at fixed support, both slope and deflection both will be zero, but at free end, what is free end over here? B. At free end, both the slope and deflection will be maximum or not equals to zero. So this is in case of cantilever beam. Now in case of simply supported beam, suppose this is our simply supported beam. Suppose this is a point load capital W, this is A, this is B, and I am assuming this is our point C. I am applying a force capital W. So the axis will deviate like this. So what is this? This is theta A, and what is this? This is theta B, and what is this? This is the deflection at point C. One thing you must remember, in case of simply supported beam, under symmetric loading. Under symmetric loading means either UDL or load will act at mid span. Under symmetric loading, students, maximum deflection will occur at midpoint. Or we can say that at mid span of the beam. So guys, maximum deflection will occur at midpoint or mid span of the beam. In which case, under symmetric loading. Under symmetric loading means either beam is subjected to uniformly distributed load throughout the length of the beam, or load will act at midpoint of the beam. So where at support At supports, always remember deflection will always 0, but slope will not equal to 0. In case of simply supported beam, at supports students, slope will not equal to 0, but deflection will equal to 0. In case of cantilever beam at support, both the deflection and slope, both quantities will be 0. But in case of simply supported beam at support, deflection is 0, but slope is not equals to 0. One thing you must be remember over here, for maximum deflection, slope is equals to 0, or we can say that where slope of the beam is 0, at that point deflection will be maximum. So student, these are the some boundary conditions related to simply supported beam or cantilever beam. Simply supported beam or cantilever beam. Again we are proceeding on to the next topic in case of beam, and that is, generally we all have gone through the equation, and this is equation is known as equation of elastic curve. And in equation of elastic curve equation, generally there is a equation we all know that EINA. What is NA stand over here? NA means moment of inertia about neutral axis. D square y over dx square is nothing but what? Bending moment about a particular section. EI d square y over dx square is equals to moment. Which kind of moment over here? Bending moment. In case of beam, we will talk about only and only bending moments over here. EI d square y over dx. In some state competition, they will directly ask about the equation of elastic curve for deflection of beams. If you will integrate first time this equation, integrate EI dy over dx, if you will integrate this equation will give mxx dx plus constant of integration. After solving this equation, or after calculating the value of constant, this equation will represent, or this equation will known as slope equation. This equation is known as what? Slope equation. If you will again integrate this slope equation, you will get EI y equals to what? mxx dx plus integration of what? c1 dx plus integration of what? Or simply the constant, integration constant c2. After calculating the value of c2, c1, c2 we will get from applying the boundary condition which we have discussed in our last slide. c1, c2 are integration constant. The value of c1, c2 is calculated by using the boundary conditions we have discussed in our previous slide. So guys, this after evaluating the constants, this equation will give you Yeah, this equation will represent what? Deflection equation. What? Deflection equation. Again, from this equation, if I differentiate this equation, means dqy over dx cube, this will give you what? Dm over dx, and dm over dx is nothing but this is the f. This is what? F. If I'm again differentiating this equation, ei d4y over dx4 is equal to what? Is equal to df over dx, and df over dx is nothing but w. What is w is representing over here? W is nothing but w is over load. W is over load intensity. W is what? W is over load intensity. And what is this F? This F is the shear force. Once or two, three times in ISRO exam, they have asked about these two relations. They have asked about these two relations. Even in 1 year, they asked from these three equations, which of the followings are correct? 1, 102, 103, or all are correct? So our answer will be all are correct. So students, moving forward to the next topic, means here we have discussed the equation of elastic curve, and now we will discuss about the shape of elastic curve, either linear elastic curve or parabolic elastic curve or circular elastic curve or a straight line. See students, deflection of beam is a very important and interested topic. After knowing the deflection of beam, you will be easily calculate the natural frequency of vibrations. And vibrations, for a mechanical engineer, vibration is a very challenging task for balancing purpose. Now, shape of elastic curve. Students, our next topic is nothing but shape of shape of shape of elastic curve. Shape of elastic curve. In previous slide we have discussed about the equation of elastic curve. Now moving forward to the next topic, that is what? Shape of elastic curve. That is what? Shape of elastic curve. So one by one I will take example over here. After knowing the shape of elastic curve, we will calculate the deflection easily. In some problem I will tell you in what kind of problem. So first example, suppose this is a cantilever beam and I am assuming at free end there is a bending moment of magnitude m is acting over here. Suppose the length of the beam over here is capital L. I'm assuming this is point A and this is point B. If load will act or moment will act over here, the curve will deviate like this, and this is what? This is nothing but this is our elastic. This is what? This is our curve, elastic curve. And if I draw tangent to this elastic curve, this tangent will give the value of slope over here, and this vertical gap or deviation will represent Bimax, or we can say that delta B means deflection. What? Deflection. What, guys? Deflection. So we all know about shear force and bending moment. If I talk about, in case of cantilever beam, always remember the shear force and bending moment at fixed support always not equals to 0. Always not equal to 0. They must have some magnitude x fixed support. Bending moment at point A is non-zero, and bending moment at point B is again non-zero over here. So students, what I am doing here, two things you must remember over here. At fixed support, in case of cantilever beam, at fixed support, both the shear force and magnitude both will not be equal to 0. Both will not equal to 0. Here at free end, a moment is acting of magnitude capital M. So we can say that bending moment at point B will not equal to 0. Since no transverse shear force is acting over here, the shear force at point B that will equal to 0. So we are concluding over here, if at free end if at free end shear force is 0 and bending moment is not equals to 0, the shape of elastic curve is circular arc. The shape of elastic curve is what? Circular arc. This is example